Okay, thanks, Stephen, and thanks everyone for joining us here. And I hope have been enjoying some of the talks today at the MeepCon. So yes, as Stephen said, I'm currently a postdoc at Stanford, working with Professor Shan Wifan. And today I'll be talking about some general elements regarding laser modeling, gain media modeling, and also some of the recent laser problems we have been looking at. So I'll start by kind of a general overview of how to model gain media and lasers, especially it's very different from the standard modeling of linear systems that a lot of people are familiar with. The nice thing is that it's all implemented in Meep. And I also look at two kind of recent problems we have been looking at, the question of stability of large periodic structures, and also some question of possibility of having exceptional point lasers above threshold. So you'll see how much we can go through depending on the time. So first, we need to understand a little bit how to model gain media, and especially in this case, multi-level atomic media, as well as lasers. Now, we start first by kind of reminding everybody of the standard equations that you use to model linear electromagnetic systems. So we start with the Maxwell's equations that relate the magnetic field and the electric field, and also the electric field displacement. But of course, these are not enough. You need to add information about the materials. Those are constitutive laws. In the case of non-magnetic materials, very common case, you basically need to add an additional equation that tells you what's the relation between the electric field displacement, or equivalently the polarization, and the electric field. Now, the way usually this is modeled, including in time domain simulation codes such as in Meep, you assume that the polarization is just a set of oscillators. Each one has a given frequency, oscillating frequency, and a certain line width, and they're all linearly correlated to the electric field through a coupling coefficient. Now, you see, if you solve this in the frequency domain, this is just equivalent to having a certain susceptibility with a given dispersion. And practically what you do is just you choose the frequencies and the line width just to have a susceptibility that, or like a permittivity that matches the experimental dispersion of the material you have. Now, what happens in nonlinear systems or saturable systems is that now the polarization is also can be described as a set of oscillators. The medium now can be described, the carriers are just described assuming a set of certain discrete quantum energy levels with certain population density in each one of them. And the polarization transition between each two level of them is also, as I said, follows an oscillator equation, but this time, in addition to the coupling coefficient, also depends, the scale coefficient also depends on the population inversion. So for every polarization, for the polarization of every transition between two, you also need to know what's the population inversion in these two states. Now, of course, for this set of equations to be complete, we also need to understand how the population densities evolve. This is why we couple this to additional rate equations, those are derived from quantum mechanical equations, and they allow you basically to solve the whole system. Now, before getting a little bit ahead, let's try to review a little bit the different parameters present here just to understand what's going on. So first we have the coupling coefficient sigma. So this is just an effective coupling strength between the, as we will see, nonlinear polarization and the electric field. Usually, if you assume that theta is the dipole element between the two wave functions, it's usually a vector, then sigma will just be the projection onto that vector with a certain coefficient here. Now, of course, in practice, usually you would like to maximize the interaction. So basically, you would actually want the electric field to be parallel to the dipole element. So this is what you assume. Usually, they're actually parallel. So the sigma here, instead of being a tensor in the general case, you can just assume it to be a positive scalar. Next, we have the equation describing the evolution of the rate of the rate equation describing the evolution of the population densities. And these, the important parameters are basically decay rate coefficients. So there's a pumping. So for each two levels, we have a pumping rate from the lower one to the higher one, and this is supplemented externally. This is what you do in laser. You have to pump the system to make sure that you can actually put more higher densities on the higher energy level. And then we also have the other way around, we have non-radiative decay rates from the higher energy level to the lower energy levels. So those are kind of the important parameters that you need to model these kind of systems. And to understand even more what's going on, we can actually try to solve this equation in a simple case, which is the case where we assume that all basically the fields are just oscillating at a single frequency. I'd like to highlight that this is not in nonlinear systems, it's not always true. You can excite a system at a given frequency and that with having higher frequencies. But in this case, it's actually very useful to see what happened in that case to understand what's going on. So first, we start with the polarization. So we assume we just have a two-level system. That's enough actually to understand what's going on in the general case. So the polarization in this case, you can solve it in the frequency domain. And what you have is, again, the polarization is proportional related to the electric field. But this time, the coefficient, the proportionality coefficient here is related to the population inversion, as I mentioned before. So this gives you kind of an effective susceptibility, which if you compute the imaginary part, you can clearly see that actually you can actually control whether you have positive imaginary part or negative imaginary part, so whether you have loss or gain by controlling the population inversion. And that is mostly commonly known. You can actually have gain if you make sure that you have a positive population inversion, meaning that the population density and the higher energy is actually larger or higher than the density on the lower energy level. That's why you need actually pumping to be able to achieve gain. Now, moreover, actually, the population inversion here is also itself depends on the electric field because they're rate equations. And we can actually solve them in this case, again, the steady state for this two-level medium. And actually, we end up with a relatively simple equation that we can actually understand. Well, first, the key point here is that you see that you actually have a saturable dependence on the electric field, meaning that actually for very strong electric field, the population inversion actually goes to zero. And this is actually something that is very crucial, and we'll see that later. It is very crucial in lasers, because as soon as you start laser, you actually need the population inversion to decay for the system to stay stable. If you don't have this dependence, you always have a large gain, so the system is going to become unstable. The fields are just going to continue to grow. We can also identify some very important parameters that actually we're going to use later to actually model all our system. The first one is the unsaturated population inversion. So the unsaturated population inversion, we call it here D0. You see it's proportional to the total density carrier. So you can increase it by, of course, having higher or larger carrier density. And also related to the pumping rate, you can also increase it by increasing the pumping rate from the lower state to the higher state. Importantly, we also have actually population inversion relaxation rate. It's actually just the sum of the pumping rate and the non-radiative decay rate. And this parameter is actually very important. As we will see in some of the examples later, it's actually important to understand the stability. The stability of some certain laser systems would actually also depend on the value of this relaxation rate. Now, one thing we can already see, as we said before, in order to have gain, you need to have positive population inversion. So in this case, positive D0, which you can see is guaranteed if your pumping rate is actually larger than the decay rate. And this gives us like our first kind of intuitive result is that if you want to have gain, you need to make sure, of course, that your pumping rate is larger than the non-radiative decay rate. We can combine the two previous equations just to get kind of an effective susceptibility that we can easily understand. We have the dispersion, the polarization dispersion that we described at first. And then we have the saturable part where you have the unsaturated pump, the dependence on the intensity, as well as the population inversion decay rate. Now, as I highlighted before, and I'm going to highlight it again, this is only in the case where your system has only one main frequency component. In practice, it's not guaranteed. You need to check that. There are some stability ways to do that, which we will see in some of the examples. Or in general, you can just run the time domain simulation and make sure if your system actually has mainly one frequency component. Another thing is that this is only, of course, just the nonlinear part, just the gain part. Of course, in systems, you also have linear susceptibilities that you need to make sure that you're adding. Now, the nice thing about is that all of this is actually now implemented in Meep kind of relatively recently, especially due to a lot of work by Alex Surgeon. You can actually check the archive paper that has kind of a lot of details, some of the things that I explained here and even more. And there's actually a very nice tutorial explaining how we can input the different parameters. So in Meep, actually, you can choose any certain number of energy levels, and you can input any kind of parameters, the ones I described, any kind of parameters that you want. So Now we understood how to model gain media. Now let's move to understand how to understand and model lasers. Now in the semi-classical picture, laser is basically a gain medium, which we just described, plus a resonator. Now a resonator is basically just in principle, at least theoretically, just any arbitrary structure or cavity that's open. In practice, you'd like to make sure to design a cavity that has low loss to have good laser properties. But in general, any passive cavity with loss, either intrinsic absorption loss or radiative loss due to the openness, would have a set of resonances. Those are just defined as the eigenvalues of the operator. Right? In this case, for example, the Maxwell operator written for a fixed polarization. Now, since we have laws, this operator is not Hermitian. So the eigenvalues are actually complex. In particular, they have to be on the lower half of the complex plane for stability and passivity reasons. The real part actually represents the standard resonant frequency, and the imaginary part represents the loss. Now, just as a quick note, I want to highlight, so since the resonant frequency is actually complex, this means that the corresponding eigenmode is actually divergence. It has actually exponential divergence outside of the scatter. And this is why a lot of people call them quasi-normal modes, because you actually can't normalize them easily. And this led to several issues. But in our case, actually, this is not going to matter because, as we will see in a second, in laser system, we're only interested in the modes that actually hit the real axis. So the modes are normalizable, everything is fine. This is exactly what you do by adding gain. So if you take now your passive cavity and add some gain to it, so the gain removes the loss or reduces the loss. So what happens is that if you compute the resonant frequencies of the system as you put in more gain, what happens is that these resonant frequencies now move closer to the real axis because the loss is reduced. And what happens is that a lesion occurs when actually first resonance hits the real axis. This is basically the first lesion threshold. Because if you think about it, now if you have now a solution on the real axis, right, it means that actually you have a solution of this problem at a real frequency. You have a solution without any external source, of course, other than the pump that you already put in the gain. So this means that now you have a solution, electric field solution, without any external source other than the gain. And this is basically what a laser is. Now, one thing you will quickly notice, if you just follow this linear equation, you can actually multiply it by any scalar. So this does not give you any information about the amplitude or the intensity of the laser mode. But if you remember what I said before, in actual gain systems, you really need the nonlinearity. So as soon as you hit threshold, as soon as you hit the laser threshold, you have now non-zero fields. So meaning that actually your gain susceptibility is nonlinear, meaning that your operator is nonlinear, meaning that you can't just scale the solution. So basically it is the nonlinearity, the nonlinear susceptibility that determines the strength of the electric field, of the laser electric field, once you hit the threshold and go above threshold. And as I highlighted before, the nonlinearity is important because as soon as you hit threshold, the pole actually can't go above the real axis. It needs to stay below for stability reason. And this is what is guaranteed by the nonlinear susceptibility. When the nonlinearity kicks in, it guarantees that the laser solution stays on the real axis even as we put in more and more gain due to the saturation. So this is kind of a semi-classical picture of how laser works. Of course, if you start putting more and more gain, the other modes are also going to get closer and closer to the real axis. And if a second mode hits the real axis, then we say that we move from a single mode laser solution to a two-mode laser solution, and so on. Now, this kind of nice or relatively simple picture of understanding laser as resonances moving to get into the real axis one after the other has kind of been formalized recently in the so-called steady-state ab-initio laser theory, or SALT, which is actually valid under certain conditions, especially when the difference between the laser frequencies is large enough, which allows basically to solve now laser systems using just frequency domain simulation. Now, as I said, this kind of picture of only having independent mode that lays one after the other is only true in certain conditions. In general, you can, of course, always solve the time domain simulation equations, like use Meep, and make sure to see actually what happens, because there's a situation where you can actually move to a chaotic regime that you can't actually describe by this kind of SALT theory. So that's nice. Now that we have understood both how to model gain media as well as lasers, we're going to move to certain examples. But before moving that, I would like to highlight an important point in nonlinear systems, which is the fact that units actually matter. For people who are just only using linear systems, usually don't care about units. You run your simulation, and only at the end you scale everything to make sure that you have the units that you want. But in nonlinear systems, this is actually not true, because you have nonlinear dependencies. So if your units are not correct, the simulation is not going to give you the right results. You can't scale everything back just at the end. So you need to make sure that the units are correct. There are different conventions. If you want to use Meep, everything is explained very well in the tutorial. Theorists always don't like to actually kind of carry all these constants, Planck constants and other constants. So they just use natural units. So they normalize everything to make sure it's in natural units. And this gives a certain number of important parameters that actually will be the main parameters to describe lasers, and that we will use in the examples later. We have the inversion, the population inversion in two-level medium, which we call here D. We have the external pump, the D0, which is the external pump, which is already described before. We have the inversion decay that I already described before. And then we have the gain line width. So the gain line width, which is just determine the line width with the gain in the two-level medium. Okay, so now that we have understood both how to model the gain medium, how to understand laser, let's move to an actual example, which is actually the one in the Meep tutorial. So we started with a very simple cavity, the most simple 1D cavity, which is a slab. So this is just a 1D slab with a mirror on the side. And of course, in the simulation, make sure that you have outgoing boundary conditions, for example, by putting a PML. So here we put a two-level atomic medium. And of course, we make sure, if you want to actually have gain, that the pumping rate is at least slightly larger than the non-irradiative decay rate. Now, to do the simulation, we just kind of initialize the simulation with an arbitrary non-zero field, then let it evolve and wait for steady state. And once steady state is reached, we can actually just compute, take the Fourier transform of the field to see what are the different frequency components. Now, in this case, what's obtained in this case for the given pump straight, you can see that actually the Fourier transform gives actually two nice peaks. So you can say that we have a two-mode laser solution. In general, you can actually just change the pump strength and see how the laser intensities change, which is shown in these two plots. You see that as we increase D0, when we reach the value of 0.06, a first mode starts lasing. We have a non-zero intensity. And as we keep increasing it around this value, 0.08, a second mode starts lasing. And even at larger values, third mode starts lasing. So this kind of validates, the picture I just described before. The nice thing is that all kind of the different simulations give the same result, whether Meep, whether kind of an in-house time domain simulation, or whether the salt frequency domain solutions. Okay, so now that we have understood kind of the general properties of gain media lasers, let's move to some of the very recent examples we have been looking at. And the first one is actually a question of lasing in extended, very large, even infinite periodic structures. There have been a lot of interest recently in actually trying to understand these periodic surface emitting lasers. So the idea is that you're trying to make a large surface area periodic lasers. People are trying to use them for different applications. But there have been a question has been raised, which is actually, what are the conditions under which you can actually obtain a large area single mode? There's actually a fundamental reason why to think this may not be actually possible. The reason is the following. If you think about a resonator, you know that the number of resonances involved typically increases with the size, right? Because the mode spacing is proportional to the inverse of the size. That is very clear in the limit of an infinite periodic structure. We all know that the modes are described by band structure. So the band structure is just a continuum set of resonances. So this is the limit of an infinite structure. You have a continuum set of resonances that are all involved in the process and all in principle can participate in lasing. Now you can already see that this kind of poses fundamental problem for single mode lasing. Imagine you start lasing with a given mode at a given wave vector, let's say the band edge. Now in the limit of a very large extended periodic structure, you actually have a continuum of modes. So actually you think that as soon as you increase the pump slightly, all the other modes nearby will also start lasing and you lose your single mode. So this kind of seems to suggest that actually single mode lasing may not be possible in the limit of a very large periodic structures. And this is the question we're actually trying to tackle here. Now, what has been done before on the computational side, a lot of people have been looking at these systems above threshold. Since simulations are costly, especially time domain simulations, a lot of people have been just using single unit cell simulations. But as you just understood now, actually, this simulation cannot guarantee that the lasing solution is stable because you do not take into account the other wave vector that can in principle lase. Of course, experimentally, a lot of people have been realizing these surface emitting lasers. They have seen single mode, but also they have seen instabilities as you increase the pump. And it is not clear why or from where these instabilities would come from. There are actually multiple potential sources. It can be either, you manufacturing disorder, surface roughness, and others. It can be the fact that you have a boundary, or it can be what they just described, which is the fact that you have a continuum of mode that would fundamentally prevent single mode lasing in the limit of law structure. Now, to solve this problem, it's important to understand that this is just a stability question. This is just a stability question. So we have a Lason solution, right? A Lason solution in a periodic structure, and you're trying to understand, is it stable or not? To do that, we can just do the standard linear stability analysis process, which is you have a steady state solution of a nonlinear equation, which, as we said, is the laser equation obeys a nonlinear equation. To understand where it's stable, you add a small perturbation, a time-dependent perturbation, you linearize your system, and then you end up with a stability eigenproblem. By solving this eigenproblem, you can find the sigmas, which would tell you whether the system is stable or not. If all the eigenvalues have negative real part, it means that any perturbation would actually end up decaying in time, so the initial solution is stable. If you have at least one eigenvalue that has positive real part, it means that if you have some noise, which you always have, at least one component of the noise would end up growing, and the system is not stable. So it's kind of a general linear stability procedure, which you can apply to the laser nonlinear system. This has been done kind of not too long ago by Stefan Rotter and others, where you can apply this linear stability procedure to the Maxwell-Bloch equation, the nonlinear equations, and you end up with an eigenvalue problem that would determine the stability. In this case, it's a quadratic eigenvalue problem. But this is not a problem. You can always solve it as you solve standard eigenvalue problems. Here, A, B, C are operators that depends on your steady state solution, on the Lason solutions. And the psi here is just, as I said, the perturbation would, here in this case, described as electric field polarization as well as the inversion. Now, this is general for any Lason solution. The key point to note is that actually for periodic structures, which is the problem we're interested in here, the stability eigenproblem is itself periodic. So meaning that now you can apply Bloch theorem to the stability eigenproblem. So you can assume that your perturbation actually have a wave vector. And then you can actually solve your linear stability eigenproblem at a given wave vector of the perturbation. So now instead of having to solve the eigenvalue problem for the whole extended structure, you now reduce it to actually a single unit cell simulation, but you need to make sure that you solve it for every wave vector possible of the perturbation. Now, this gives us kind of a neat way to check the stability of large periodic structure by bringing it back to unit cell simulation, but making sure that you probe all possible aperiodic perturbation by checking the stability at all the different wave vectors of the perturbation. So this is nice. Now we have this procedure, numerical procedure, we can apply it to systems. This is what we do here. So we can start with the first 1D example. So this is a 1D photonic crystal, kind of a toy model for a distributed feedback laser. So I'm putting here the band diagram, the lowest two bands, the frequency as a function of the wave vector. You can see, of course, that we have the band gap. Here we put in actually a two-level gain medium with a central frequency pretty much on top of the band edge. And what we do is that we actually compute what is the threshold, what is the pump required for each mode on this band to hit threshold, which is shown in gray here with the right axis. I see actually that the lowest pump, that the lowest needed pump for a mode to reach threshold is actually on the band edge, as expected, because it's the one that actually has the lowest loss, meaning that the band edge mode is the mode that's going to laze first. Now, the fact that it's going to laze does not mean it's stable, because again, just to emphasize it again, you actually have all these modes that can in principle laze, and you would think that as soon as this mode starts lazing, all the other ones are going to laze, and you're not going to see a single mode. But what we do is that we can apply the stability procedure we said before. We assume this is a single mode lasing, and then we check the stability, including all the possible wave vector. And the results are example of the results are here for a given population inversion. So what I'm plotting here is actually the sign of the stability, the real part of the stability eigenvalues as a function of the perturbation wave vector as a function of the pump strength, knowing that the pump threshold of the band edge mode starts here. Now, the nice thing that we see is actually, contrary to what the intuition you get from linear system, the system is actually stable. Even though there's a continuous mode, the system is stable for finite amount of pump after a threshold. And then it instability reaches starts at a certain point. Now, the reason why actually this works is all because of the nonlinearity. Now, think about it again. If this mode starts lasing, what we said before is that the susceptibility is going to change. So this mode is going to actually start eating the gain from the other modes, and it's going to start eating the gain with a profile that actually is similar to the nearby mode. So basically, once this mode starts lasing, it eats up the gain from the other modes, and the threshold for the other modes is actually pushed. And this is why you end up actually having a single mode stable. It is because of the gain saturation, the gain saturation that eats up the gain from the other modes. Now, we also confirmed, so all this, as I said, is like the frequency domain simulation of our stability eigen problem. We also confirm it by doing time domain simulation. What we do is that actually we initialize the structure with the Lazen solution, we add certain noise, and we see whether the system gets back to the Lazen solution. So since we can't simulate infinite periodic structure, what we do in the time domain is we assume a supercell with a given size, right? And we truncate it and we put periodic boundary conditions on the supercell. Now, of course, in practice, what does this mean is that it discretizes the number of allowed wave vector, right? And confirm actually the time domain simulation, the instability starts as soon as one allowed wave vector hits the instability region. This is when the instability starts in the time domain, which actually matches very nicely with the expectation from our stability eigen problem. And you see that as you increase the number of the size of the supercell, you can actually get closer to the threshold found by the stability eigen problem. Now, this is nice, but there's actually one important question. Is it true that actually you can always have your single mode Lazen solution stable near threshold, or is there a condition for that, right? And actually, we work out this problem analytically. So we're able to linearize the eigen problem near threshold. I'm not going to go into the details, but we're actually able to do it. And the kind of a key takeaway from this is that in the limit of small loss, small absorption loss, the stability condition near threshold is actually a very simple condition. It tells you that the band curvature, right? The band curvature needs to match the laser detuning sign, right? In 1D structure, it's always true if your central line width is inside the band edge. If your central line width is inside the band edge, then the band curvature of the band at the band edge, it also has the right sign for the stability, which is what happens here. We can also look at more complex examples, like 2D examples. We try to track some special kind of resonances, so-called bound-in-continuum states. This is what we did here. So what we've taken here is that we have a 2D structure, right? 2D periodic structure, kind of a cylinders, dielectric cylinders, and a mirror, backed by a mirror. And we plot here is we plot a band, a resonant band above the light cone, in absence of absorption pump, and also at the threshold. So if you look at so this is the real part of the resonances, and this is actually the imaginary part, the inverse of the Q factor. And you can see that, in absence of absorption absorption loss and presence of radiation loss, you see actually that for certain wave vector, you actually have zero loss, zero radiative loss. Those are the so-called bound-in-continuum states. So they're bound states because they have zero loss, but they are inside the continuum. And the idea is that we're trying to check, can we actually have stable Lazen BICs? So you see, we have here 3 wave vector. One of them is at 0 wave vector. So it's kind of a trivial BIC because enforced by kind of a symmetry. But also we have non-trivial BIC and non-trivial wave vector. So here, as I said, we put some 2-level atomic medium here with a certain gain frequency, central frequency. And we compute again the pump threshold for every mode here. And we see that the lowest pump at threshold is actually for this second BEC, which means that this will be the first Lazen mode. So this mode will be the first to reach threshold starting for lower pumps. And the question again is this mode stable? So we perform the same procedures before, and the results are shown here on the right. So what we do is we check the stability of that second BIC Lazen as a function of the pump strength and here the wave vector perturbation. And we see actually that in this case, it is actually also stable for a finite amount of pump. So the threshold starts here and instabilities arise much later. We also confirm that with time domain simulation. These have been performed actually with Meep, again with a supercell. And we see that actually the Meep time domain simulation matches nicely in the sense that for this given strength, we see a single mode Lazen, and as we start at the instabilities, we move to second mode Lazen as well as a third mode Lazen. Now, one thing is that actually with this example, we can also confirm our analytic condition for stability near threshold. So in this case, actually, the band curvature was chosen with the right sign, but actually we can change it. So here the band curvature is actually positive, and we put a positive laser DQ in. However, if we change actually the center gain to actually move it higher, to have a negative sign, we actually see, which is the case shown here, that actually, so arbitrary close to threshold, there's always instability. So here I'm plotting the real part of the eigenvalue, and you see actually there's always a positive real part as close as possible to threshold, meaning that in principle, this kind of structure would not actually, you would not have fundamentally, you would not have single mode laser for an arbitrarily large structure. So this kind of concludes this part where basically we're able to kind of answer this fundamental stability question, rigorously answer this fundamental stability question of periodic lasers. Basically what we saw is that due to nonlinear effects, which you need to take into account, periodicity does not prevent single mode lasing, even in the limit of infinitely large structure, as long as certain conditions are met. In practice, of course, instabilities can occur for other reasons, such as boundary effects or manufacturing disorder, and these need to be taken into account carefully. Okay, so now we can kind of conclude the second problem we tried to talk about, and now we're going to move to another interesting example that people can also try to check and confirm with time domain simulation in MEEP, which is the lasing at exceptional points. So for those not familiar with, exceptional points are basically just special kind of resonances that occur when actually two resonances of an open system coalesce and become degenerate. But also their eigenfield is also becomes degenerate, so that the operator becomes defective. So this is different from standard degeneracy. In standard degeneracy, you have the same resonance frequency, complex frequency, but the eigenfields are different. Here, actually, you have the same eigenfield, so the operator is not diagonalizable anymore, and it becomes defective. So they're having a lot of interest in trying to see, can you actually achieve exceptional point lasers? They're having a lot of work on that for multiple applications. But if you see a lot of, especially the theoretical work, actually only talk about exceptional points below the lasing threshold, and then they add gain, and then they see what happens. But if you think about it, and consider what we said before, as soon as you start lasing, the operator changes, the susceptibility changes due to the saturation. So if the system was at EP before threshold, it's not going to be at EP after threshold. So you can make sure that you design the system with an EP after threshold. So this should be part of your design. And of course, the question of, can you obtain it? Can you obtain such EP above threshold? How can you characterize it? And is it stable? So I'm going to start with presenting a simple couple mode theory analysis of the standard dimer, where you have actually two resonances that are coupled with a given certain loss rates, but also they are pumped by external pump. But this time you make sure you assume that actually we have a nonlinear gain saturation. Okay. Now, without going into the detail, the bottom line is actually we can solve the steady state solution of this couple mode theory, and we can find the real solution, which will be the lasing solution, the real frequency solutions, and there are the two types of solutions. First, they're PT broken solutions that actually have a constant frequency, and then they have PT symmetric solutions, two PT symmetric solutions that actually have two different frequencies. Now, at the transition between the two phases, these two modes actually coalesce, and you have actually an exceptional point. And you can find analytically the condition of the exceptional points above threshold, which is basically you need to have a specific ratio of the unsaturated pumps in the two cavities. Now, as you can see at the EP, you have a kink in the frequency, as seen here. You have actually a kink when you transition at the EP. You also can check that the output power, you can compute the output power of the systems, and also confirm that it also has a kink, which will be another characteristic of an EP laser. So let's now look at an actual example by doing full wave simulation, frequency domain simulations. In this case, a very simple example: 1D two coupled slabs, right? That we pump. We pump each one of them, and of course, we assume we have a two-level atomic medium here. So by using frequency domain simulation, we can compute the threshold for this systems, which is shown here in actually pluses, and we see that actually it matches very nicely with the threshold predicted by CMT. Now, in general, this represents a phase diagram predicted by CMT, where we see that we have a line for the EP, and above threshold, it needs to be above threshold to see an EP. Below threshold, we can also have what we'll see as a virtual EP. So it's an EP that you will not see because it's below threshold, but you can find it numerically, and it's very useful to understand certain things that's happening when you are actually in this region. Okay, so now we have this phase diagram. Let's actually try to see, do a full wave simulation and see what happens if you actually go to the EP. So first we start by pumping the first cavity from here to a given value, right? With the guarantee that we are at the nonlinear EP. And then after that, we start pumping the second cavity until we hit the exceptional point and go above. The results here, so these are frequency domain full wave simulations, both the latent frequency and the latent power. So we see that we start here actually with a PT broken solution. It's very clear from the mode profile. So basically, we mostly pump in one cavity. So the solution is actually not PT symmetric. And as you increase actually the pump in the second cavity, you hit the actual exceptional point, which is very clearly seen by kink in the frequency here and the kink in the output power. And the mode profile, the latent mode profile now actually becomes kind of more symmetric. And then when you go actually after you transition to the PT symmetric phase, and you can see it actually clearly from the field profiles, it actually has pretty much a symmetric feature. Okay, so this kind of confirmed from full wave simulation the predictions from CMT, and we see that we have the transition with an EP clearly characterized by the different kinks. Now, as I said, it will be actually nice to see what happens actually if you pump the system in this line and see what happens at the virtual EP. So now we pump the first cavity to a lower value, and then pump the second cavity and follow actually this line. So what happens is that you start actually laser in the PT broken phase, but then actually when you hit the red line, you actually hit threshold. So actually the laser turns off. So this is the output power. The laser turns off. But actually, technically, numerically, you can actually keep track of this nonlinear solution by solving for negative intensity. Of course, this is not a physical solution at all, but it's very nice to track it numerically because it allows you to see a negative intensity and see a kink associated with a virtual EP. As I said again, physically, experimentally, what we see is that the laser turns off and then turns up again. And this has been already talked about kind of a few years ago. It has been labeled as a suppression and revival of laser, and it has been kind of broadly associated with EP. But this is, I think, the first time when we clearly highlighted actually related to a nonlinear EP that's kind of hidden below threshold. Okay, so this is kind of a nice analysis of exceptional point laser. But again, I just want to highlight all those were frequency domain simulations. So we did not check actually if there are other modes that actually would make the system unstable. So this is why it's important to do stability analysis, which we talked about before. And this is what we did here. So we did the same procedure. We assumed that we had a single mode exceptional point laser, and then we check the stability analysis. And here we're showing the plot as a function of the pump in strength, as a function of the inversion decay rate. And we see basically the conclusion from all of this is that actually the exceptional point can be indeed stable as long as you make sure that the inversion decay is actually large enough. Okay, so this gives us a clear stability condition for the EP laser. So it is not always stable, but it can be stable as long as you're careful with the inversion decay rate. Okay, so this kind of completes the general analysis of exceptional point behavior. How can we characterize it in terms of the frequency and power kink, as well as confirming its stability? Before that, there's actually a very interesting thing that we can check actually that we can do with this exceptional point, which is we can try to operate it as a parametric amplifier. So assume that we have our exceptional point, laser here, that we're pumping it, that actually emitting a laser frequency. We can actually try to see what happens if we scatter some light of it, some very weak light of it. So in the limit of very weak field, actually we can also generate another idle field. So this is just a parametric amplifier. And the limit of weak signals, you can actually just solve or find the strength of the different transmitted and reflected fields by solving coupled nonlinear field equations. So those are wave coupled equations. So you can actually solve them and compute the transmission. And this is what we're showing here: the transmission at the same frequency at a different input frequency. And this is actually the detuning from the laser frequency. So first you see actually, of course, you have a divergence at the laser frequency. And this is, of course, expected because at the laser frequency, you have a resonance on the real axis, meaning that the Green's function diverge. So, of course, your signal will diverge. In practice, you will not actually hit this limit because as soon as you hit it, saturation is going to kick on, and then you're going to actually have your transmission to be saturated. Now, the important thing we see is actually for here we're plotting transmission for different pump rate, where the EP is actually shown in orange here. And we clearly see, as expected, since at the EP we actually have two coalescent resonances, we see that actually the divergence rate is actually quartic now instead of the standard quadratic divergence that would be associated with single resonance. So that would be kind of a different and very interesting signature to make sure actually, or to check if you actually have an EP laser. So this concludes kind of the third part I want to talk about, which is a different kind of novel laser that a lot of people are interested in, that you can also actually check what happens with time domain simulation. So we gave the general conditions to obtain it. We confirmed the stability by frequency domain simulation. And we also saw some of the characteristics in terms of the kinks and also the potential quartic rate when used as a parametric amplifier. So with that, I think I'm pretty much done. It's already time. So before ending, of course, I'd like to thank different people who helped in these works. Of course, Stephen Johnson, who was my advisor and who pushed me to work through a lot of these problems. Alex Surgeon, who I mentioned, was actually the main developer for implementing multi-level atomic media in Meep, which had been very useful in all the time domain confirmation simulations. And Luke Stone and Adi Pick, who have been actually very helpful in understanding and developing the EP laser work. And with that, I would be very happy to answer any questions you have.
Thank you, Mohammed. So I think there's already one question in the Q&A from Simon Bilodeau. Asks, for these large spatially extended structures, what is the impact of disorder in the local gain medium on the stability analysis?
So disorder mainly would actually just change your loss rates. Right, so usually, I mean, the simplest way to model disorder, you just assume that it adds additional absorption, right, to the loss to your loss rate, and this will mostly shift a lot of things. So this will mostly shift a lot of other things. That's first what happens when you add disorder in general systems. In the special case of BIC, so as I said, BIC is a case where you have actually zero loss. This would actually remove the BICs. So one of the interesting things, as we said, is a lot of people interested in BIC. So in absence of any absorption loss, these actually have zero decay rate. So basically have zero radiative loss. When you add surface roughness, when you add a disorder, first it removes, so the loss is not exactly zero, but also it scatters them off. It scatters them in different directions. So that's another effect. So I'm not sure if that answers the question. So it's mostly effect on the decay rates, which would shift kind of the exact results. So the local gain medium, I'm not sure what you mean by the local gain medium.
I'm guessing it means just disorder within the structure.
Yeah, so of course, one thing to highlight is that here, of course, the gain is, you can have a gain profile, right? So the gain has, of course, here you have a gain profile. It doesn't have to be constant throughout the structure, right? You have X dependence. I made sure to highlight it. So anyways, so here in general, of course, the pump, the gain medium doesn't have to be constant throughout the structure. So if that's what meant by the profile.
So are there any questions from the room? Yes, Ryan in the back.
So very, very interesting talk. Nice results, Mohammed. I'm interested if you've considered studying the quantum statistics, particularly just below thresholds of these points, right? That could be very interesting, especially like in the context of squeezing that definitely occurs right below threshold, right? And might be related to your numerical solutions there.
So are you referring in general or specifically to the exceptional point case?
Well, in general, your theory, but the exceptional point, I actually don't even know what would happen. So if you had an answer, I'd be interested.
So okay, can you repeat the question again? So you're trying to ask what happens. So when you add the quantum statistics below threshold at the EP systems, is this a specific question?
Yes, that's the specific question. Yeah.
Okay. So just to make sure, so this is an important question. So one thing that kind of try to highlight is so the EP is not everywhere. So the EP is, at least in this case system, is at a specific, so here the EP is actually at a specific line, right? So actually, if you're below, if you're outside a specific line, you're not actually at an EP, right? So even if you're latent, so here this is not an EP. The structure here does not have an EP. Actually, the two modes don't have the same frequency. And here the same, and below threshold the same. It's only at this point that you have an exceptional point. And this is kind of what's different from a lot of what people have been doing before. So people have been doing before, they have a passive cavity, it has an EP, right? And then they put gain on it, and they see what happens to the latent solution. But when you put in gain, you change in the susceptibility, you change in the operator, so actually you don't have an EP anymore. So your question would be, if you design an EP below threshold, or which you can, which we're most basically we're looking at here, what would be the quantum statistic? And more generally, I would assume even above threshold, you would actually
slightly above threshold, you'd still retain. Yeah, that's right.
Yeah, exactly. So even above threshold, the same question. And I would say this is in general related to the question of the line width, and it's actually a very interesting question, or noise actually at the EP. This is something that we have not looked at. And actually, it's hopefully some of the follow-up that we can. So the question is, what happens to noise at the EP, and what happens to the line width at the EP? That's something that will be very interesting to check. It's definitely kind of on the pipeline of things to do. Is what happens to the noise at the EP, what happens to the line width at the EP, whether above or below threshold.
So a few years previously, my other student Adipik, who Mohammed mentioned at the end, did a lot of work on generalizing laser line width theory for the quantum noise, but that work doesn't work at the EP. The eigenvalue predictions basically they fail at an EP. They just diverge, which is it won't actually diverge. But yeah, so that's something we want to revisit.